One of my goals this year is to build highly performant tiny language models. And as I was working through some tasks to prepare for that, I realized I needed a refresher on how cross-entropy loss works. Specifically, I was trying to visualize with a concrete example how small batch training can lead to noisy gradients. That's going to be a separate blog post that is based on a Gemini Deep Research report. But in this notebook, I went back to chapter 5 of Fastbook, and I walked through the code and the concepts and dove a little deeper to kind of build intuition around how cross-entropy loss works. So here is my cross-entropy loss explainer. We're going to start by looking at some real data. So we're going to look at the pets data set, which has 37 categories of pets. And I'm fine-tuning it on a couple of epochs. And the error rate goes down to about 8%, just so I can look at some predictions. So I grab one batch from the data loaders. The inputs are a batch size of 64, or has a batch size of 64, 3 channels, and 224 by 224 pixels. So these are our images. If we look at Y, and we look at the shape in particular, we have 64 items. And each item is an index corresponding to whatever the class is predicted, or sorry, not predicted, the target for the pet. So the first image is whatever the pet is at index 23. Second image is whatever the pet is at index 13, so on and so forth. So these items are all between 0 and 36 because there are 37 categories that are possible, 37 classes in our data set. So if I pass this batch into the learner.getPreds, then I get back a bunch of values, and specifically I get back 37 values. And if I take the sum of these 37 values, it equals 1.0. So what that tells me is that these values are percentages, or rather probabilities, that the given input batch of 64 items, sorry, first item of the input batch of 64 items is one of these classes. So if we look at preds.shape, we'll see that it's 64 by 37. So for every one of our 64 images, we have 37 probabilities, one for each class. And the maximum probability is going to be the one that is our predicted value. So this is looking kind of at the top-down approach of like, what do we actually get back from a real trained model when we're using cross-entropy loss for multi-class classification. And what I mean by that is we have a single label, but that label can be one of many categories. So that's kind of an intro example, just to orient our minds around what this looks like for a real classification data set. From here on out, we're going to work on some toy data that's easier to conceptualize. So what we're going to look at is a binary classification example where I have two columns, column 0 and column 1. Column 0 is for some category 0, it could be cat. Column 1 is some other category, it could be dog. And I have 6 items in my batch, and I'm just creating some random values. So what I'm creating here is I'm creating some fake values for the activations that are coming out of the model. Now these activations are not yet probabilities. They're just some numbers, right? So we have, 4.4, 0.5, negative 0.3, so on and so forth. And what we're going to do as we build up this cross-entropy loss function is we're going to convert these values into probabilities where for each batch item, the probabilities add up to 1.0. So we're basically saying what is the likelihood, or what is the probability, I should say, that this class is predicted, or this class is predicted. Another way to think about it is how probable does the model think that this image is of class 0 or of class 1? Okay, so the first thing we're going to do is we're going to start with one function that squeezes values between 0 and 1, and that's sigmoid. Now, if we just take the sigmoid of our activations, while it does achieve one desired result, which is each value is now between 0 and 1, it does not achieve our full desired result. The sum of each row is not 1.0. So here we have 0.66 plus 0.56. Here we have a total of about 0.49. Here that we have a total of about 1.2, so on and so forth. So the problem here is that sigmoid is only taking into account that given activation. What we want to do is we want to incorporate some sense of relative kind of probability between these two values. Like these two values need to be considered at the same time in our equation, because we want to say that out of these two values, this one has a certain percentage and this one has a certain percentage. So what we find in the book is that we talk about how taking the difference between the class activations and then passing that through the sigmoid does give our desired result. So we end up with probabilities that sum up to 1.0 across the classes for each batch item. So here I'm going to say, here's my class 0 activations minus my class 1 activations. And we do the sigmoid of that. And then on the other hand, we have my class 1 activations minus my class 0 activations. And we take the sigmoid of that. And now we can see that because we have incorporated both activations, we now have probabilities that add up to 1.0. And to look at that concretely, I'm just going to add these two tensors together, and I'll see that I get a final tensor with 1.0s across. So that's great. At least I know it works, right? So we have this concept of the difference between activations passed through the sigmoid gives us probabilities. If the first one is first, class 0 is first, and then we're subtracting class 1, that gives us the probability of class 0. If class 1 is first, and then we subtract class 0, that gives us the probability of class 1. So why does this work? I'm going to approach it a couple different ways, and well, 3 different ways. The first 2 ways are mathematically, and then the third way is more conceptually. So you can kind of pick whichever one makes most sense. The first approach I'm going to take is I'm going to write out my equation of sigmoid. So if I have sigmoid as a function, and I input x1 minus x2, that translates to 1 over 1 plus e to the negative x1 minus x2. So this x1 minus x2 is the input, and sigmoid is 1 over 1 plus e to the negative input. So we have x1 minus x2, a negative sign, and it's e to that power. So what I'm going to do is I'm going to take this denominator, 1 plus e to the negative x1 minus x2, and I'm going to expand that into a fractional form. So I have 1 plus 1 over e to the x1 minus x2. And then I'm going to think of this as 1 over 1 plus that fraction, so I can kind of combine terms into a single fraction. So how does this work? Well, 1 times e to the x1 minus x2 is e to the x1 minus x2. 1 times e to the x1 minus x2 plus 1 is this numerator. Okay, so originally I had 1 over that denominator. The denominator expands out into this form. So I'm going to plug that denominator back in here. And because it's 1 over that, I have to flip it. So what I get is e to the x1 minus x2 over e to the x1 minus x2 plus 1. So all I've done is I've rewritten this e to the negative x1 minus x2 as a fraction, combined the terms, and taken its reciprocal, and it's still equivalent to sigmoid of x1 minus x2. With some help from Gemini, I realized that what I can do now is I can multiply this term by 1. And I'm going to choose a particular fraction to use as 1, and that fraction is going to be e to the x2. So e to the x2 over e to the x2 cancels out, so effectively I'm multiplying this by 1. But by doing so, we're going to see how we get our desired result. So walking through this step by step, because I'm multiplying fractions, I just multiply the numerators together and I multiply the denominators together. In the denominator, I distribute the e to the x2 to the exponent function or value term as well as the plus 1. So what I get is e to the x1 minus x2. When we multiply it by e to the x2, that becomes a plus x2. And then e to the x2 times 1 is just e to the x2. And then on the numerator, we get the same type of action. x1 minus x2 multiplied by e to the x2 is adding that x2 in the exponent. So what happens here? x2 negative plus x2 positive cancels out. So I get e to the x1. Same thing happens down here. Negative x2 plus x2 cancels out. So I get e to the x1. And here I have my final result. So I have the activation, e raised to the activation of class 0 divided by the sum of e to the activation of x1, which is our class 0, plus e to the raised to the activation of our class 1, which is x2. And this is the softmax calculation for the first class probability. All right, so what portion of my total activation is the first activation? That's what this tells us. So the chapter goes on to say the second column, the probability of it being a 7. So in this example, we were predicting, class 0 was a 3 and class 1 was a 7, would just be this value here subtracted from 1. So let's write this out. The sigmoid of the difference between the second and the first class probabilities is 1 minus the sigmoid of the difference between the first and the second class probabilities. So all of that is to say that sigmoid of x2 minus x1 equals 1 minus sigmoid of x1 minus x2. So I'm taking this value here and I'm subtracting it from 1. I have this summation of exponents in the denominator, so I'm going to make an equivalent form of 1 here, so I have the same denominator, so I can just do a subtraction. And what I see here is I have e to the x1 plus e to the x2 minus e to the x1. That leaves me with e to the x2. So this is now e to the x2 over the summation of e to the x1 plus e to the x2. So this is now the probability of our class 1, our x2, because it's now represented as a ratio of the total activation exponentiation. So what I've basically done here is I've started out with sigmoid and I've ended up with softmax, because softmax is the e to the whatever class that you want the probability for divided by the sum of e to all of each one of the class activations that you have available. And in our case, there's 2. So if I look at this here and I do 1 minus sigmoid of the first difference, I can see that I get the probabilities for the second class. All right, so that was one approach. That was my first approach, so it was not very clean, but we got there. And then as I was staring at it more, I realized that there's actually a simpler way of looking at this. So we're going to start again with sigmoid of our difference of classes. And we're going to do 1 over 1 plus e to the negative x1 minus x2. All right, so here's our input, e to the minus x, and x, our input, in this case is x1 minus x2. I'm going to now expand the exponent term in the denominator. So the difference of exponents can be written out as a fraction of exponents. So e to the x1 minus x2 can be written out as e to the x1 divided by e to the x2. And because it's 1 over that, I can flip it. And so this term here in the denominator is now e to the x2 over e to the x1. So let's plug that back into our denominator. 1 plus e to the x2 over e to the x1. I see e to the x1 is the denominator. So instead of 1, I'm going to do that same trick again. I'm going to rewrite 1 as a fraction. And I'm choosing the fraction so that I can have the same denominator, so I can simply add across. So I have e to the x1 over e to the x1. plus e to the x2 over e to the x1. E to the x1 plus e to the x1 in the denominator is e to the x1. E to the x1 plus e to the x2 is our numerator. So the denominator in the sigmoid is this term here. And if we plug that back in here, 1 over that, we just flip it, and we get our softmax for our x1 activation. So this is a much cleaner, 4 steps, a lot less algebra, or I guess arithmetic. Well, no, this would be algebra going on, so a lot more straightforward. Definitely the more preferred option. So mathematically it made sense, but I was still hung up on this idea of why the difference, right? Why do we, why is it that the difference in activations, leads us to the probability of that activation? So that ended up in quite a long conversation with Gemini. We ended up talking about what are logits? Where does the concept of logits come from? What does it mean in terms of its relationship to sigmoid? What does logits mean in the context of multi-class probabilities that we are dealing with here? What does logits mean in the binary class situation? So I've kind of come up with these 6 takeaways from my conversations with Gemini. First off is that sigmoid is designed for a simple binary outcome, A and not A. So we can't use it for more than 2 classes. Okay, so that's idea number 1. Idea number 2 is that the difference in logits is a difference in quote-unquote learned evidence between the 2 classes, right? So how much more evidence do we have in favor of one class than another class based on how big the activation is that the model produced? So the value x1 minus x2 represents the log odds of class 1 relative to class 2. So in terms of the actual logit function, it is the log of the probability of class 1 divided by the probability of class 2. And because we have 2 options, right, A and not A, probability of class 2 is just 1 minus probability of class 1. Now, let's look at it in a different way. Suppose we had a difference of 0, right? So the logits x1 and x2 are equal. If we pass that difference through the sigmoid of 0 is 0.5, and that means both classes are equally probable. So if we go back up here to our sigmoid function, here is 0.5, and here is 0. So if we passed in a difference of 0, that would mean that each class, class A and class B, or class A and not class A, has a 50% probability, right? So that was kind of a key understanding for me to understand how this difference in binary class and sigmoid all kind of interact with each other. Okay, let's keep moving on. Sigmoid is the inverse function of the log odds or logit function. So sigmoid of 0 is 0.5, and the log of 0.5 over 1 minus 0.5, which is just 0.5, so that's log of 1, equals 0. So this only works when we're dealing with binary classification, because the probability of class A, 0.5, is just the probability of class B, which is 1 minus the probability of class A. Let me actually say that again, sorry. The probability of class B is 1 minus the probability of class A. So this logit function, probability over 1 minus probability, that only works in the binary classification sense when it comes to working with sigmoid. So softmax is not the inverse function to the logit function, so only sigmoid is. Even still, we call binary classification activations logits, and even more than binary, we have 37 classes. we still call them logits because we eventually turned them into probabilities. So this idea of logits and probabilities being related, the fact that we end up with probabilities is why we call them logits. That was my understanding. The softmax function is the general template for all classification problems. For the special case of exactly two classes, this general formula mathematically simplifies to be identical to the sigmoid and the difference between the logits. So it's in this unique case of activation of class 1 minus activation of class 2, so this difference in activations, difference in logits, translating to the probability as the softmax function. This is only possible because we have binary classification. The reason being, let's say we had three classes, right? Dog, cat, bird. If x1 is the activation for dog, and x2 is the activation for cat, and x3 is the activation for the bird, well, x1 minus x2 is not the whole story, right? The probability of dog is not 1 minus the probability of cat. The probability of dog is 1 minus the probability of cat plus the probability of bird. So as soon as we have 3, we can no longer use this idea of like a difference between the logits to give us the softmax. Okay, for 3 plus classes, the model's final activations are still called logits. However, they no longer have a simple interpretation as the log odds of a single event. We think of them as some kind of learned raw or uncalibrated scores that softmax converts into a valid probability distribution. So this difference in the binary sense is giving us the same value as just, the probability of one minus the probability of the other. Or I should say the probability of class A is 1 minus the probability of class B. And that binary classification relationship is the only reason we can use this difference in logits to give us the softmax. So those were kind of the 6 takeaways that I took from my conversation with Gemini. So let's go back and let's return back to the process of building up cross-entropy loss. So now that we have probabilities, what we now want to do is we want to select the probabilities that are associated with the batch item and the target that we are trying to reach and calculate their logarithm. And we'll see why in a second. So our activations, the textbook says, after softmax are between 0 and 1 and sum to 1 for each row in the batch of predictions. So I have my raw activations. I pass them through softmax. I'm taking the softmax across the columns. So this is e to the x1 divided by e to the x1 plus e to the x2. If we add these across, we get 1.0. So we have our desired distribution and probability values. All right. So how do we want to use these values, right? We have these probabilities, like what does that mean for helping the model learn to do its job? So what is the job that we want it to do? Well, we want the model to penalize its predictions when they are wrong. So the target wrong means the target label is not predicted with the highest probability. Some other label is predicted with the highest probability. And we want to especially penalize the language model when it's wrong and confident. So the target label is predicted with a very low probability. On the other hand, we want to encourage the model to pick the right class confidently. So we want it to give the largest probability to the target label, and we want to increase that probability as high as we can, so it's very confidently predicting that. So we achieve this two-pronged behavior by taking the logarithm of the target probability, because the logarithm, as we're going to see, has the same behavior about penalizing wrong predictions, and especially wrong and confident predictions, and incentivizing confident right predictions. So let's go here and let's just make up some target classes. So for the first batch item, the target class is class 0, so first column. For the second batch item, it's class 1, the second column. Class 0, class 1, class 1, class 0. So these are our targets. What we're going to do now is we're going to index into our probabilities using the batch item index and the probability column index. Because our activations, which are now passed through softmax, so these are really probabilities, because they have 2 dimensions, we're going to need 2 indexes. So our first index is going to index into the rows, and that is just a range 6. So it's just 0, 1, 2, 3, 4, 5, right? 0, 1, 2, 3, 4, down to 5. Our second index, which is indexing the columns, right? 0 or 1, is going to be picking out whichever target column that it needs to pick out. So if we look at this, cool. So if we look at this, our index goes from 0 to 5. So index 0 is our first row. The first target is column 0. So our first selected probability is 0.6025. Second row has target of 1, so it's 0.47 or 0.4979. Third row has column 0, right? So third row is column 0, 0.1332. Row 4 is column 1. Row 5 is column 1. Row 6 is column 0. And so we can see that. So what we have done is we are basically asking the question, what did the model predict as the probability for the target label to be the correct label for this image, right? And that question is answered by this indexing operation, right? What is the probability, so softmax activations, that the model picked for each batch item for the target label for that batch item, right? So all of that is happening in this indexing. So why is the logarithm suitable for our situation? So let's first print out torch.log as a function. As x is very close to 0, the logarithm of that value goes down to -infinity. As x gets closer to 1, the logarithm of that value goes up to 0. And 0 and 1, why are they of interest for us? Well, that's exactly the range for our probabilities, right? Our probabilities can be a minimum of 0.0 and a maximum of 1.0. But this is still not quite what we want. When we think about loss function, we want to minimize the loss when our model is correctly predicting targets, right? So as the model correctly predicts targets, the loss should get lower and lower. But here, if a probability is 0 for the target, the loss is getting lower and lower. This doesn't really work for our loss kind of objective. We want this flipped. And so that's what we'll do. We'll just multiply this by -1. And now we have behavior that matches our loss function objective. So when the model predicts the target label with a very high probability, our loss function is going to get closer and closer to 0. When the model picks for the target label a very low probability, close to 0, the loss function skyrockets, right? So very, very incorrectly confident predictions are going to be penalized exponentially. And then very, very confident predictions that are correct are going to be incentivized positively, right? The loss is going to be very low. So here are my softmax activations. I pass my softmax activations through -torch.log. And now I get the loss values. Let's look at some of these loss values, right? So here, the target label has a very low, under 50% probability. And for that reason, we have penalized it with a relatively large loss. Here is a very confident, very wrong prediction for the target label. And we can see here that it's penalized even more than this, right? On the flip side, here is a somewhat confident but correct probability for our target label. And so relatively to these two, this is a very small loss, right? It's like 1/4 the size. So we can see, going back to our desire here, our expectation, we want to penalize the language model's predictions when they are wrong and confidently wrong, and we want to encourage the model to pick the right class confidently. And that's what we achieve by this negative log function. All right. So again, each one of these values, so 0.6025, here's 0.6, 0.25, and that's about 0.5. Here's 0.0034, 0034, maybe up down here, and it goes up to about 5 point whatever, 5.69. All right, so let's look at how these are implemented in PyTorch. So PyTorch has this negative log likelihood loss, and what it actually doesn't do the negative log part, but what it does is it does the indexing part and the multiplying by -1 part. So if I run this here, I give it my softmax activations, I give it my targets, and what it does is that it just indexes into that 6x2 matrix based on the column that the target is in, and plucks out those probabilities and multiplies them by -1. Now, if I pass the log of those activations, then we'll see that it does the indexing with targ, multiplies it by -1, and we get back our loss function. So this is effectively our loss function using torch.log and f.nll loss. Cool. So another excerpt from chapter 5. As long as the activation columns sum to 1, as they will if we use softmax, then we'll have a loss function that shows how well we're predicting each digit. Therefore, making the activation for the correct label as high as possible must mean we're also decreasing the activations for the remaining columns, right? So if this activation is 0.5067, the other probability has to, looking at the wrong one. If this probability is 0.6025, the other probability has to be less than 0.5, right? It has to be 0.3975 or whatever it is. And this holds even for more than 2 classes, right? If we had 10 classes and the first one had a probability of 60%, the other 9 are going to add up to 40%. So none of them individually are going to beat out this highest probability value. All right, so we've seen kind of the components to it. We've seen that we take the activations, we pass it through a softmax, we pass that through a log, we index according to our targets, we take the negative value of it, and we get our loss function values. This is what we call cross-entropy loss. So the combination of all that is cross-entropy loss, and we can call that with our raw activations, right? These are not passed through softmax, and our target values. We have a reduction of none, so it keeps the dimension, and we can see that we have our loss values here. Another comment from the book, taking the mean of the negative log of our probabilities, so taking the mean of the loss column, gives us the negative log likelihood loss, which is another name for cross-entropy loss. So what we could also do is we could pass reduction equals mean, and now we have our scalar loss value, that you would see on a loss curve during training. So I mentioned earlier that one of the motivations for me going back and looking at the cross-entropy loss was to understand, how small changes in a batch size and in the actual activations and the probabilities, how those changes propagate down through the gradients that are resulting from this loss calculation. So I kept going in the textbook, and they talk about the gradient of cross-entropy loss. So we're going to recreate with code this following explanation. So an interesting feature about cross-entropy loss appears when we consider its gradient. The gradient of cross-entropy AB is just softmax A minus B. Since softmax A is just the final activation of the model, that means that the gradient is proportional to the difference between the prediction, which is softmax A, and the target, which is B. This is the same as mean squared error in regression, since the gradient of A minus B squared is 2 times A minus B. So we still have this proportional to the difference between prediction and target. Because the gradient is linear, that means we don't see sudden jumps or exponential increases in gradients, which should lead to smoother training of models. So what I'm going to do is I'm going to calculate the gradients using the torch backward method. So let's add a requires grad flag to our activations. Let's do a sum first for our loss. Let's then do a backward pass, so back propagation, and we can now see that we have now gradients for each one of our terms. So now let's go back to this definition in the book. The gradient of cross-entropy is softmax A minus B. So that should be pretty straightforward to implement. So I want softmax of activations minus the targets. And because I have just a single 1D tensor of targets, I want to create the target is 1, the other class is 0. So I'm going to run that through here. Okay. So now we do the activations, softmax applied across the columns minus the targets. And we run that, and we get these values here. So if we look up here, negative 3975, positive 3975, positive 5021, negative 5021, right? That matches here. Negative 8668, positive 9966, that matches here. 5959, negative 0.6339, that matches here. So this way we've been successfully able to recreate the gradient of cross-entropy loss using softmax activations minus the target. Okay. Looking at one more wrinkle, since ultimately we want to have the mean value of the cross-entropy loss, or at least that's common, how do we handle that? So I have reduction equals mean. So now this is 1.805. Calculate the backward pass. And if I look at my gradients, now they are considerably smaller. So all I have to do here is I have to do my manual gradient, which is softmax of activations minus the targets. Except now I just divide by the batch size, which is 6. And then I get the same result as Torch's automatic gradient. So, in conclusion, this was a really helpful refresher for me because now I can experiment on this and answer questions tangibly. What happens if we have a small batch and one of the predictions is very wrong? How much does that affect the gradient, right? Versus if we had a larger batch and one of the predictions was very wrong, how much does that predict the gradient? And we, of course, would expect that as the batch size increases, 1 or 2 outliers impact on the loss, and therefore the gradient is going to be less. That was originally the question. This now allows me to actually, intuitively understand what exactly is happening. Activations change. That means the probabilities change. I index into the probabilities with the targets. I pass it through the logarithm, take the negative value, take the average. That's my loss. So this was a very helpful kind of explainer, refresher. Now I feel a lot more confident, moving forward with my experiments with language modeling. Another thought that I've just, been having recently is that next token language generation is fundamentally a classification problem. So the classes are the tokens in the vocabulary. The model predicts the most probable next token. It learns to favor target tokens during training because of cross-entropy, just like it would learn to favor target classes and learn to disfavor the wrong classes. And so ultimately, how this behavior is reinforced in language modeling is intuitively the same as we saw in this kind of like image classification type of problem. So that's it for this video. Thank you so much for hanging until the end. I will see you next time, and thanks for watching.